So I'll have the next group load their presentation, and I will go ahead and introduce this team. I also see Dr. Calin, Tarau. I think most of you have already met with him virtually this week. He gave a seminar on Tuesday, a very interesting project. His team worked with NASA JPL on a space mission project, and he's also working and helping us on this project. So this project is titled Design and Fabrication of an Additively Manufactured Vapor Chamber Heat Exchanger for Space Applications. And Dr. Calin, Tarau, and also Mike Elllis, our collaborators from Advanced Cooling Technology, a company located in Lancaster, Pennsylvania, and also supported by the NASA grant we received. So this project is to explore a way we can modify a vapor chamber heat exchanger design. Has been developed by ACT, and we're trying to utilize the resources we have here on campus, the metal 3D printer, to redesign and to make it the system compatible with the 3D printing, that we can eliminate some of the shortcomings of have to fabricate multiple parts and assemble them. So the goal was to design the system that can be printed all at once to simplify the system and also explore the capability that we can improve the design and see whether we can further enhance its performance. So I will turn over to the team, and I see the slides. So if you're ready, you can start your presentation, and please hold your question to the end. But feel free to type in through the chat box. We'll answer them at the end of the presentation. And yeah, so please go ahead, and if you're ready, you can start.
Good morning. Can everybody hear me?
Yes.
Yeah.
Right.
Very good.
My name is Jelani Guise. I'm here with my teammates.
Ibrahim Alghamdi.
Yasser Alghamdi.
Drew Gray.
And as Dr. Shu mentioned, this is the design and fabrication of an additively manufactured vapor chamber heat exchanger for space applications. So we're going to start with our outline. We're going to begin with the introduction, move on to the objectives, literature review, design. Then we're going to wrap it up with the future works, conclusion, references, and acknowledgements. So beginning with the introduction and project description.
All right, so in spacecraft, the thermal control system is an essential system that keeps all the spacecraft component as well as the crew of the spacecraft within an average temperature during all stages of the mission. Helps ensure that the component within the spacecraft function correctly since it changes temperature, and it could reduce the lifespan of the component if the temperature is not stabilized. And there are two types of thermal control system, active and a passive thermal control system. So starting off with the active thermal control system, this system consists mainly of thermostatically controlled electrical heaters with the fluid circuits that help transfer the heat generated by the equipment to the radiator. Active thermal control system can function as both cooling and heating device. But the main disadvantage of using active thermal control system is that it required a constant source of electrical power to function during all stages of the mission, which also means that it needs a backup source of power, which will add an additional weight to the entire system. Not to forget to mention, it's also expensive and it requires maintenance. An example of active thermal control system is the built-tire thermoelectrical coolers. The figure. So moving on, we have the passive thermal control system, which uses a multi-layer insulations, a combination of thermal coating and heating pipes to optimize the temperature of the equipment on the spacecraft. Passive thermal control system does not require a constant source of power, and it uses a different passive thermal control applications in order to get that power. And so this method was proven to be reliable, cost efficient, and it's also weightless. And an example of a passive thermal control system are metal conductions, thermal straps, aluminum ammonia heat pipes, and lastly, phase changing materials, which our projects will be based on the phase changing material technique. So I think it's good to start with using the phase changing materials. Phase changing materials are materials and substance capable of storing and releasing a significant amount of energy in form of latent heat. The way these materials and substance work is when they experience a rise in temperature, the phase changing material change their phases, and in our case, they go from liquid to a vapor form, and they store the heat energy during the process. And when the temperature falls, the substance releases the energy and turns into its original state, which is phase changing materials are mainly used for thermal absorption for duty cycle applications, and the reason for is using a phase changing material is that it does not lose effectiveness when it undergoes a repeated cycling process, which is really good when it comes to a long spacecraft mission. Moving on. And so we know modern electronics and technology have a miraculous amount of complexity packed in a very small spaces, which will eventually generate a large amount of heat, and that heat can reduce the lifespan or even destroy this. And phase-changing material heat sinks will transfer the heat to the radiator, which will disband the heat and radiate it into space. Phase-changing materials are also commonly used for thermal management electronic system, and they can store energy to stabilize the component of the temperature. And they are good at storing energy when comparing it to a other passive thermal control techniques.
Now we're moving on to the literature review.
So conventional PCMs have inevitably the disadvantage for low thermal conductivity. So in most typical PCM-based heat exchanger, they're usually embedded with a solid heat transfer structure, and that's to enhance the overall thermal conductance. For example, using aluminum fins as shown in these two figures. And these additional solid structures add lots of weight, which typically consumes around 50% of the system mass, and that makes it very difficult to achieve high mass ratio. So in 2015, NASA set a goal to reduce the overall mass of an onboard thermal storage system, because in terms of spacecraft, reducing weight can save exorbitant amount of money. Next. So to reduce the mass, Advanced Cooling Technologies, ACT, has developed several innovative heat exchanger with thermal storage capability that integrate phase-changing material within a vapor chamber. So by changing or replacing the solid heat transfer medium with a two-phase working fluid, both overall mass and thermal resistance can be reduced significantly. So under the program of development, two different heat exchanger concepts were developed and tested. The primary heat exchanger joins a microencapsulated PCM, as shown in the figure, and the microencapsulated PCM beds, which can be used as a heat storage medium as well as a wick structure for the two-phase working fluids transportation. And the second PCM-based heat exchanger incorporates numerous rectangular drawers charged with PCM into a vapor chamber. And the second concept is going to be our main design for developing this project. So in here, we're going to go more in depth in the second concept, which is the two-phase heat exchanger with PCM drawers. So it's basically a developed heat exchanger that integrates phase-changing material PCM within a vapor chamber. And this heat exchanger consists of a multiple of ultra-thin drawers charged with bulk PCM, and the interior and exterior of each of these drawers are wrapped with a screen mesh, which serves as a wick structure to transport the working fluid to the heated region. And depending on the heat sink and on the sink temperature, developed heat exchanger can either function as a thermal capacitor or a two-phase heat exchanger with thermal storage capability. Slide. So When the environmental temperature is lower than the PCM melting point, the device will operate in the heat exchanger mode, which is similar to a standard vapor chamber. And the way vapor chamber works is whenever heat is applied anywhere to its surface evaporator, the device will vaporize the working fluid, and then the heated vapor will move quickly through the inside of the vapor chamber, where it's found somewhere cooler than its boiling point, which most likely is going to be in the top surface, or in our case, in the bottom surface of the figure. And then the heated vapor will condense, then travels back by a wick material to the heated source. And when the environmental temperature is higher than the melting point of the PCM, the device will operate in the heat capacitor mode. And in this mode, the PCM will keep storing heat in the form of latent heat diffusion until the sink's temperature drops below the melting temperature of the PCM. Then the heat stored within the PCM will be released into the heat exchanger, and then the device will go back to work in the standard heat exchanger mode.
So our objectives for this project. We wanted to analyze and simulate the phase change material heat exchanger to see if its performance could be improved by altering its structure through its height with number of drawers. We wanted to redesign the phase change material heat exchanger to maintain the optimal performance while becoming manufacturable through 3D printing. We wanted to fabricate a functional prototype with additive manufacturing techniques.
Jelani, we're having a tough time hearing you. Can you get closer to the mic, please?
Okay. I'll go over the objectives again. We wanted to analyze and simulate the phase change material heat exchanger to see if its performance could be improved by altering its structure. We wanted to redesign the phase change material heat exchanger to maintain the optimal performance while becoming manufacturable through 3D printing. We wanted to fabricate a functional prototype with additive manufacturing techniques. Is that better?
Yes, it is better.
Yes, it's better.
Okay. Then our constraints, the design must be at maximum 12 by 12 by 12 inches. That was the size limit for our printer. It must be printed in raging steel. The working fluid must be compatible with the selected metal, and then the mesh has to be installed manually. So moving on with our design.
So these are two figures of our design. The figure on the left is our assembled vapor chamber design from ACT remodel to fit the design specifications with wall-to-wall drawers, complete with separately attached front and back walls. The figure on our right is our PCM drawer design from ACT redesigned to fit the design specifications. Meshing will be added to the outside of the drawer to facilitate capillary forces. With the revised model, there have been some changes that we've made in order to make the system more functional and compatible to 3D printing. Using Creo 5.0 software, we were able to create a scale model of the PCM vapor chamber to be printed and tested. We're using COMSOL to model the meshing structure for the drawer and casing. So our drawers. The drawers have now been updated to a 45-degree angle at the top and the bottom, which you can see. This allows us to maintain PCM thickness while also allowing us space for a fill tube without increasing the height of the drawer. The drawers are now wall-to-wall. This compensates for the PCM volume loss in the angle of 45 degrees at the top and bottom of the drawer. This allows for the removal of spacers. The original design had spacers built into the walls to space the drawers out in between. But the drawers are no longer required to be printed separately, saving time and money. You can go to the next one. So the figure at the bottom, this represents the print distance that is compatible with our printer. If it's larger than 2.5 millimeters, then it will require a support structure to 3D print. While the figure on the right, this shows the printing angle at which the drawers were tested, and after 45 degrees, the material begins to deteriorate, with extreme deterioration coming at 25 degrees. The drawers, as you can see at the bottom, has a small hole. This is the fill tube, which has been retrofitted with a press fit cap. This is airtight and a compatible technique for material restraints. There was a 9% increase in the mass ratio by decreasing the wall thickness from 0.05 centimeters to 0.04 centimeters, and the drawers now touch the top and bottom of the casing at its center for ease of mesh installation.
So here for the drawers, after we altered the drawer geometry, it was essentially to verify that the functionality had been retained within the drawers, and it was still capable of returning the working fluid from the evaporating side from the condensing side to the evaporating side. So to do that, we worked with this formula right here, this inequality. Delta PC is the capillary force. Delta PG is the pressure loss due to gravity. Delta PV and delta PL are the pressure changes in vapor and liquid, respectively. And so, as long as the capillary pressure is larger than the combination of these other pressures, then at the given height, the working fluid should be able to return to the evaporating side. And so, this is our calculations for our particular heat exchanger. So another consideration that we had for the drawers was the print orientation. And for our case, the print orientation affected the internal geometry of our drawers, which also affected the performance of our drawers. So one of the first print orientations that we had was printing the heat exchanger horizontally, as shown below, as shown in front of you. The image you're looking at is the drawer sliced in half, and you're looking at it from this side. Now, the pros to printing it horizontal, it required less powder because there's a lower height, and there's less powder required for the print. And also, therefore, it's a quicker print, and it has more internal volume. I'll get to that in a second. And the cons were it requires support structures. Now, what I mean by more internal volume, if you look on the left side of the image, you can see that the outside of the wall and the inside of the front wall are not parallel, but the inside has an angle. That angle is 5 degrees. And the purpose of that angle is to help facilitate the removal of powder once the printing is complete. So there will be powder within the drawers. And so without that angle, it would be difficult to remove the powder from within. Moving on, here and highlighted in green are the locations in which support structures would be necessary if we printed it horizontally. So as my teammate Ju mentioned earlier, anything spaced more than 2.5 millimeters apart needs to be a support structure if it's going to be a flat. And so with the drawers that we printed, the angle gave us the capability to not have internal support structures, but now we have external support structures in between each drawer to support the top wall. And then again, at the bottom of each drawer, we would need support structures on those angled surfaces. And the purpose of that is not to support the weight, but to help with heat dispersion during the printing process so that there's no deformation because the heat is concentrated in one spot. Now, here's our alternate print orientation, which is vertical. So the pros of this vertical printing is there's no need for support structures, which would really increase the time of preparation, especially if it had to be hand removed. But the cons to this were the longer print because it's vertically taller, so it would take longer to print. It will require more powder because of its vertical height. And then there is less internal volume. And let me explain this. As you see earlier, I had a 5-degree angle at the top of our drawer, but now we have a 45-degree angle. And the purpose of this, again, is because any surface that is more than 2.5 millimeters apart without a support structure needs an angle. And so what we had to do was increase that angle from 5 degrees to 45 degrees. Otherwise, we would have to have internal support structures. And the problem with internal support structures is they'd be near impossible to remove. So here at the bottom, we have a comparison of the volume change and the heat storage capacity that would come with these different orientations. So 0 degrees would be, we had to have no angle, which is just the controls comparison. 5 degrees, which is the horizontal, and 45 degrees, which is vertical. Those volumes are the internal volumes inside the drawer, so the empty space inside the drawer in which PCM will be filled up. So the more PCM space we have, then the more heat storage capability. And so as you can see, 0 and 5 degrees have a comparable volume, whereas 45 degrees has a considerable decrease in volume and then consequently heat storage capabilities.
So for the drawer versus wicking structure, drawer wicking structure versus the grooves. We were considering using grooves instead of a wicking structure to see if that would increase the capillary force of the working fluid. We found that the grooves are only compatible when there aren't gravitational forces and produce subpar results, with the wicking structure still proving to be the better of the two. Below are the listed equations for capillary pressure of the wicking structure and grooves respectively. The first equation is for the wicking structure, and that produces about 661.142 newtons, while the grooves in the second equation produce about half that at 330.71 newtons.
So here's our casing. This is how the heat exchanger will come out of the printer, with the drawers and then the top, sides and bottom. It will require a separate front and back plate, and this is for the installation of the mesh. The way the mesh would be installed is you would take a sheet of mesh, you would fold it in half, and you would slide it onto each drawer on one side, and then spot weld it to connect it to the drawer, and then go to the other side, fold it, put it in there, and spot weld it again. And then the same will be done for the internal walls of the heat exchanger. So the PCM and working fluid that we selected for the PCM pure temp 18, which, as the name implies, has an 18 degrees Celsius melting point, and it has heat storage capability, a capacity of 192 joules per gram. It is consistent, repeatable performance over thousands of thermal melting solidifying cycles. It is 100% renewable and readily biodegradable, produced from agricultural sources, not petroleum. And then the working fluid we chose was methanol, which is the most common working fluid for heat pipes. It is also compatible with our raging steel. If you look at this chart right here, it shows some of the favorable qualities of methanol, and particularly its high latent heat, which you see at the bottom. For our project, we wanted to do a sample print, but it was cut short by the inability to access our school facilities at these times. But just for that, the reason the goal of the sample print was to print 2 drawers to confirm the support structure locations, then attempt the powder removal, and then cut open to examine the internal structure. So now we're going to move on to the simulation and modeling.
So for the simulation, we used COMSOL multiphysics to study and analyze the thermal behavior of the redesigned vapor chamber. So in order to compute any results for the vapor chamber, first we had to come up with some assumptions, which are the gravity effects are neglected, heat transport take place mainly by evaporation, condensation, and convection of vapor. Heat transport in the wick is simplified as conduction with an effective heat transfer coefficient. And lastly, constant material properties are assumed except for the vapor density. And for the model setup interface, multiple physics were added to the geometry of the model. First, non-isothermal flow laminar multiphysics interface for modeling convective and conductive heat transfer together with the evaporation and condensation mechanism, laminar flow in the vapor chamber itself, and then lastly, heat transfer in the wall, wick, and the vapor. And for the geometry and operating condition, we use aluminum vapor. So we assumed we were using an aluminum vapor chamber and also aluminum mesh. And for the working fluid, an acetone, so it can be compatible with the aluminum material. And then the heat load is equal to 100 watts. External temperature is 285 kelvins. So this is the vapor chamber after modeling using COMSOL multiphysics. And as you can see from the figure, it consists of the casing, which is the vapor chamber itself, the PCM drawers, and in our case, it's going to be empty during the simulation. And then lastly, the screw mesh. And as you can see from this figure, it shows the 2D model distribution of temperature throughout the vapor chamber with Q equal to 100 watts. And the temperature at the evaporator section is around 350 Kelvin, which is the bottom surface of the vapor chamber. And it sharply declines when it reaches the condenser section, which is approximately around 320 Kelvin. And if you convert these numbers, it's almost 30 Celsius degrees in temperature reduction.
Okay, so this particular project is a part of a 3-year endeavor, and we were cut short by COVID-19, meaning that a chunk of our project was stopped. That being said, we've come up with a good number of future works that will prove to be very beneficial to finishing the project and furthering its research and capability. So the future works include, but are not limited to, if possible, printing a 3D model to show to the public and test, exploring 3D printed wicking structures to grant single print capabilities, manufacturing a model that is made out of other materials. Those other materials could include aluminum, which is the original design by ACT, carbon steel, or a lighter metal alloy, applying this model to other applications outside of zero atmosphere usage. Other applications could include automobiles, HVAC equipment, or other everyday uses, creating versions on any given scale to accommodate and acclimate to any size, and finding other PCMs that are also compatible with the system and more efficient working fluids. Some more context of our project. The main purpose of this project was to prove the 3D printing and fabrication capabilities of the vapor chamber heat exchanger. Because this design can be 3D printed, it makes it less expensive and easier than trying to build everything in a manufacturing plant or even by hand. With more research done into this heat exchanger, the vapor chamber has a possibility to increase the practicality and accessibility of other forms of heating and cooling systems outside of zero atmosphere usage and revolutionize some areas of engineering. Moving on to our conclusions. Heat can build up extremely quickly in confined spaces such as human-occupied cabins of spacecraft. The primary use of this heat exchanger is for the thermal management of the cruise compartments on manned spacecraft. Devices and components being 3D printable is essential in our evolving world, and that they have the potential to save time and money otherwise invested in longer manufacturing processes. While not being able to print a physical model, we were able to successfully design, model, and simulate a working version using various softwares. The figure on our right is the depiction of our lunar lander, which is a manned cruise compartment of a spacecraft, where our thermal heat exchanger will be used. These are some of our references. And a special thanks to ACT, Calin, Tarau, and Mike Elllis. Thank you for answering questions that we had and for helping us with any problems that we came across and for giving us a wonderful tour of your facility. It was really interesting and I'd go back in a heartbeat. The second is to Kelly Gameda. Thank you for taking time out of your graduate coursework to help us understand concepts that we couldn't wrap our heads around. And finally, Dr. Shu, thank you for always advising us on the project and for challenging us to not settle for mediocrity. And I want to give a special thank you to my group mates. We weren't seeing that, we were going to end our senior year in a non-traditional way. But I want to say thank you for always keeping your heads up and having our back so we can finish this project.
All right, this is Calin from ACT. I have a question. I have a question about the fill tubes. I saw the drawers; they are not having fill tubes attached. So, is there any plan to 3D print the fill tubes at the same time with the drawers, with the whole thing?
Maybe it's a bad angle, but here the fill tubes are here at the bottom, right where my cursor is.
Yeah. So they are protruding into. Okay, so they are longer than they seem to be, right? Yeah.
Yes, yeah. It's just the angle makes it seem quite.
Okay, I understand. Thank you. That was my question.
Yeah, thank you for the question and the presentation. So we're now open for the questions from the audience. If you have a question, either type in through the chat box or just unmute yourself and ask the questions. Again, just a reminder that we noticed some of the errors during the for the survey. Please make sure you select the right project when you do the evaluation. And again, the evaluation link is in the chat box. So if you need, you can directly click that link for your survey form. So any questions for this team?
It is me again. I just wanted to clarify or to make sure the drawers are they are spaced away from the ceiling and bottom, right? We have
Yes.
some. I didn't see that, but we have some legs. 3D printing, doing 3D printing, they keep the drawers together with the whole envelope, right?
Can you show the 3D model of that?
Yeah, summer.
So, let me. Well, here it's not a good depiction, but so in the middle of the drawers,
Okay.
they're connected to the top and the bottom of the casing, and then
Very
they go at a slight angle down, to make space for inserting the wicking structure. So that's why you see a gap at the front here
Yes.
between the top and the bottom, the top and the top of the drawers and the top of the casing, but in the middle they're connected to the casing itself.
But you have a gap at the middle too. A smaller gap that on the beginning, at the edges, at the sides, but it has to be a gap for the actual screen to be inserted.
Yeah.
So there is a leg, right? So that connection between drawer and ceiling and bottom has a small length equal to the gap. It should be like that, right?
Could you repeat that one more time?
So we don't see it in the picture. In the picture, we see the gap between both ends up and down of the drawers with respect to the ceiling and bottom.
Yes.
Right? We see gaps. These gaps are decreasing from both sides as we go to the center.
Yes.
But at the center, the gap shouldn't converge to zero. Should converge to a certain value, which is smaller than at the sides, but a value equal to screen thickness. At least one layer of screen.
Okay. Yeah. So, for how the design is right now, there it is connecting at the middle and the top. So there would be almost negligible area in which there would be a very small space in between the two meshes if we insert them from both sides.
Okay. All right. Thank you.
Yeah. Do you have a side view of that drawer
A solid.
with top and bottom? Yeah. Maybe, yeah.
Okay. Yeah. So, yeah, it's we can see here, but the connection between the drawer and the ceiling and the bottom
Yes.
should be a little leg.
I
That
get what you're
leg,
saying. Yeah.
a little, like let's say 200 microns, something like that, which I anticipate the thickness of the screen would be equal to the thickness of the smallest increment, which would be one layer of the screen.
Yes.
Probably around 200 microns. Okay.
Okay. Thank you for the input.
Thank you.
So maybe you can show that in your drawing, just a side view of this. I think the previous slide, if you can go up one slide. Not this one. Can you go back? Go back one.
I think that one is a good one. The previous one. Oh, this one. No, but the one where we can see in cross section.
Yeah.
The whole. This one, yes.
Yeah.
The bottom right.
Yeah, but that one doesn't include the top and bottom casing, right?
No, it doesn't.
Drawer itself.
Okay.
Yeah,
Wait,
maybe you want. Mhm.
So
Go ahead.
we don't see that detail. We may communicate after that, after
Mhm.
this meeting. We may
Mhm.
clarify this.
Yeah.
Thank
Okay.
you. No problem. Thank you.
I saw a question from Dr. Klein. What was the most challenging aspect of your project? Trying to increase the efficiency and reduce the weight was definitely the hardest part. I would have to say, working in a group is pretty cool because everybody is able to pull their own weight. But coming together and trying to figure out different ways to increase the efficiency while decreasing the mass, because everybody came up with different ways to do it, and they might not have always it might not have always worked, or they would be in conflict with someone else's ideas. So that was probably the hardest thing.
Okay.
And then I see another question from Dr. Chen. It says, can this design be tested in a simple way to shield the heat from the device that it is trying to protect?
That's a good question. I hadn't thought about that.
Okay, so let me first explain how the device would be set up. There'd be a water glycol loop circulating the internal parts of the cabin, right, collecting heat from the different sources, be it human or electronic, and then that heat is carried through this loop to the heat exchanger, which then translates the heat from the loop to the heat exchanger, from the heat exchanger to a separate loop that's disconnected from the interior of the cabinet. And then this loop carries the heat to radiators, which radiate it out to space. So can it be tested in a simple way to shield the heat from the device that it's trying to protect? So it would the heat exchanger itself would be far enough from the devices. The heat exchanger is not pressed up against the devices. So there wouldn't be any direct correlation from the heat in the heat exchanger to the getting back into the or leaking onto the devices. If that answers your question.
Yeah, I think there are two different operating modes, as you mentioned at the beginning.
Yes.
How this one operates, how the heat is able to be conducted through one side to the other, during different operating conditions. So, that's something you have to take into account when you, place this device, near the components you want to use it for.
Yes, I get what you're saying.
Yeah. All right. So I think we're close to the time for this. So I guess maybe one question, the general question is, so what do you learned? Maybe one most important thing from this experience. This is, a collaboration with industry, and also you have been constantly communicating with our collaborator. So can anyone share your one of the most important thing you have learned through this experience?
So go ahead.
Go ahead. Okay. I would say that being in the industry is definitely different from being in school. School you're learning, but in the industry you're doing, definitely hands-on work. So it was cool to just learn about a particular type of technology and see how it was made, how the design process came about. And other applications it could be used for. So that's one thing I learned.
And then for me, the biggest part was project planning and communication. So this project, it was a full year project, and so you can't attack it the way you attack a homework assignment that's due the next night. It has to be broken down into smaller pieces, and once it's broken down into smaller pieces, then pieces have to be delegated. We have to have regular meetings. So gaining these teamwork skills, I think, was very valuable to me, and that's something that I definitely learned during this project.
Good. How about Ibrahim and Yasser? You worked on the modeling simulation part.
Well, yeah, for me, I think communication was the number one success to any project. So this is what I've learned from working on a team, and that I can implement that in the work field as well.
Okay. So you feel you have a better understanding or practice of communication?
Yeah, of course.
Team group. Okay.
As for me, modeling and as well as the simulating system, I've learned a lot about it through the project, as well as managing this project.
Okay. All right. Very good. So yeah, please, if you haven't filled a form for evaluating this team, please fill it out. It's very important for us to get feedback on their project and also their presentation. Please spend a couple minutes, click the link to fill out the survey. So I'll let you stop sharing.